camera, and the resolution is very low. So that kind of image you can get from camera of maybe 1,000 euros with this resolution. But it can perfectly see at night. It has the range till horizon, and it has also low data rate because the resolution is very low. Yeah, disadvantages is the high cost. So the good, this one I have one myself for 300 euros. It's good one for fun, but for good applications probably you need some more expensive one. Okay, the infrared, the ultrasound sensors, you know that all these park assistant cameras, they are using the ultrasound sensors because they're quite efficient, very cheap, and the problem is that they do not play on a long range, so it's up to 10 meters basically, 10-20 meters. The last, most interesting thing, which is now coming up and getting cheaper and cheaper and cheaper, and therefore in autonomous driving it's used very often now, is the laser scanners or LiDARs. So these are the examples of Velodyne laser scanners. This one now costs around 6,000 euros. It's a very good quality. It is able to reconstruct this kind of images, 3D point cloud images. And the good thing is that if you install it on your robot or on your machine or your autonomous driving car, then it's basically the device which allows you to see everything around your car. So not only directed projection of 45 degrees like with many cameras, with RGB cameras, but here there is a turning infrared emitter and sensor. Emitter actually emits the infrared pulses, and you see everything around. So that allows you to understand the full 3D map of your surroundings. So that may be very interesting, but not probably for this project, but in general it's quite interesting solution. And all this kind of autonomous driving cars that you see in the news, they are all using one of these three.
What do the colors mean in this picture? They don't look like depth, right?
No, this is not the depth. I actually don't even know what can it be. This red heat. Yeah, actually, no idea what can it be. Normally, when you get your standard point cloud from the laser scanner, you get it all in the standard grayscale. But then people are doing all kinds of processing techniques and they color it up. So, yes, question?
Recently in a conference by Tesla on the Autonomy Day, Elon Musk said that whoever uses LiDAR for autonomous vehicles is like doomed and something like that, and very expensive. So what's your take on that?
Yeah, so there is a point in this, because currently already with cameras, you can achieve a very good localization quality and very good object detection quality. So basically, indeed, placing this expensive device on the top of your car is not really a good solution, because from your two cameras on top, you can already get very good positioning of the car and object detections. So indeed, if it goes like that, with the computer vision techniques, these kind of devices will not be needed for the cars, for the autonomous driving cars. Indeed, there is a point in this. But so far, even with these devices, autonomous driving cars are not able to drive in the roads which are not designed for autonomous driving cars. So if you place a Uber car on any road in Russia, for example, or in Czechia, or even here sometimes, then you will have a lot of problems. So even with this one, it's still not solved, but it will be. Yes, question?
So I was wondering, you mentioned that they also use infrared, but how do they get rid of the disturbances caused by the sun during the day?
thing is that they use a different wavelength than the structured light. So the structured light, they use near infrared, and actually that interferes with the sun infrared light. And those lasers, they use basically the green. They are also called green lasers. So they use completely different range, and then the sunlight is not interfering with this wavelength.
And additionally, they also modulate the signal.
Yes.
So you can expect a certain modulation pattern, and that's the only thing you respond to.
Yeah, that's a good point, yes. I tried myself many of them, and I can say that there are still many problems with them. So I tried, for example, in the foggy day, it doesn't really work. So fog destroys most of the signals. I also tried it in the port, when I put it towards the water line, so I wanted to detect ships, for example. But then for some reason, first of all, the water was dissolving the laser impulses, so I could not see anything. Instead of water, it was just a black spot. And also, if I see a ship coming on the water, I was not able to see the ship. So it was somehow, I don't know why, maybe because of these small water particles above the channel, or because of this reflection of the water, but also the ship disappeared. So it's not always working. Right, so you can already from these characteristics, you can make your own decision what kind of sensors to use, depending on what you want. Is it the price? Is it the quality? Is it, are you going to work at night? Do you need to see far away? What kind of processing platform do you have? So using those limitations and constraints, you can decide what kind of sensors do you want to use. I'm leaving it up to you, so I'm not going to decide for you. Probably it's already decided, but that's just for you to understand that there is always a choice, right? So even if it's already decided, maybe you are so interested in the project, so you say, oh, okay, I'm going to use the stereo setup, for example, instead of standard one. Now, let's now proceed to some of the most conventional and standard classical techniques for computer vision that may help you in the project. And I would like to start with the segmentation technique, which is very simple to explain and also to use, but still can be extremely efficient and effective in the tasks for robotics, for example. So basically, what is the point in the segmentation? Segmentation is the process of extracting shapes from the image with specific color characteristics. Okay. It's a simple technique. It doesn't require a lot of computation, and the limitation is that it doesn't work when there are a lot of colors in the scene, and it can easily get misleading when you have occlusions or you have some clutter in the scene. So you will see later that for segmentation, sometimes it gives you perfect results, but sometimes completely unusable results. In your case, for example, if you are looking for a goalpost, segmentation success will depend on the background. If the background will be like this wall, then segmentation is sufficient. You will see your goalpost clearly. But if the background will be like some flowers or something like that, then most probably you will not be able to get a very good extraction of a goalpost. So let's see at this simple technique. So one of the simple technique is just the color-based segmentation, where you have your image, your original image, this one or this one, and then you just convert each pixel from the RGB value into so-called HSI value. So HSI means that that's the hue, that's the saturation, and this is intensity. The hue tells you everything about color. So the color component now is not spread over RGB, over these three components, but it's completely focused, that's completely compressed into the hue. And this saturation and intensity, it only shows you how bright and how saturated this pixel is, this color is. Okay, so when you convert it into this color scheme, you look in the hue. Each pixel has its own hue. And then you say, okay, I know this is the hue table. And if I am looking for some color, I pick up this color and I look I check what kind of hue value this color has. And I'm gonna look for those pixels with this range of hue, right? You can also work with different things. You can look at saturation, you can look at intensity, not only at color. So it's not only color based, but it works for any kind of things. You can also look at luminosity with chroma. Red, green, blue, it's not really interesting. Not really interesting. But these two are the most popular color scheme. So basically an example of this is such that you take an image and you say, okay, I'm interested in all yellow objects because my goals are supposed to be yellow, maybe white, but in this case yellow, right? Then you say, yellow in the HSI range or color scheme is in between 50 and 70, the values of yellow pixels. Then you say, okay, I'm gonna threshold my image for the values from 50 to 70, and then I'm gonna determine the clusters of those yellow pixels, right? So you get something like this. You get yellow here, you get yellow there, you get yellow also here. And then you say, okay, I'm gonna create blobs around those yellow clusters. So basically, I'm gonna remove everything, all the other pixels, apart from these yellow areas, and I call those blobs. And next steps I'm gonna use only those areas. So the resulting task will be a binary image. Binary image, we say, is the image where a pixel can have either 0 or 1 value, right? Yes or no. So these are the faces in this case, detected faces. And then you can do the next, basically your search space for your goalpost will be very limited. It will contain only this area, and this area. So next steps for the recognition of goalpost will be fast and efficient. Basically, you can already say that you have detected the goalpost because these areas are very small, for example. So, right? It's important to mention that the color-based segmentation is not a final technique for itself. So basically, it's not giving you the answer, where is my object? It's only giving you the answer that, okay, let's remove all the bad candidate areas and leave only good candidate areas for your further consideration. Another example of segmentation is the watershed algorithm. Watershed algorithm is, it allows you to find out not the color areas, it allows you to find out the edges between the objects. So what does it do is that, first of all, in order to apply it, you take an image and then you apply a Laplacian filter. I will tell you later what is Laplacian filter. Just let's look at the result now. This is the result of Laplacian filter. Laplacian filter extracts the pixel areas where our gradient of intensity changes very fast. So what is intensity? If we look at this image, we see that the intensity of this pixel is very high, so it's white basically, right? And then we move over pixels, and then at some point in time we see that intensity becomes to black. So we say intensity is low. In this area in between white and black, we see that the gradient, the magnitude of the gradient change of the gradient is very high, because intensity is changing very rapidly from maximum to minimum. So then we say, okay, this is the area where gradient changes. This is the area where gradient changes. This is the area where gradient changes, where intensity changes, sorry. So where intensity changes, our gradient appears to be high. This is the result. This is the picture of gradients, right? So if you look at this transition of our intensity, it's represented also here. Here our intensity change is high, therefore it's white. The funny thing is that in between this, we get some black stuff. Why is it black? We don't have any white here. That's the question to you. Yes?
There is no change in intensity.
Yeah, exactly. That's the answer. There is no change in intensity here. It's always black. And if it's no change in intensity, then we have no change in our gradient. So basically our gradient is low. So that's how gradient works. Here's the first step of the color segmentation. Use the filter to create a gradient map of the image. When this map is ready, we do the following. We can also look at our gradient in this way, just for you to understand what kind of hills here, right, and water, hills and water here. If we cut this image, this is the gradient map. If we cut it in this line, we can look at the gradient values here over the line, and we can build up those gradient values as this, right? So you can see that the gradient value is very high here. It's this one. Then it gets lower, it gets to black,